All right, in this video, I want to analyze using calculus to sketch the graph of f of x equals 3x to the 2/3 power minus 2x. Now, there's a lot of moving parts here, so I want to go through this problem thoroughly and slowly. Now, there's going to be information that we could gain from the function itself. X-intercepts, y-intercepts, domains, asymptotes, whether or not there's any discontinuities, holes, jumps, vertical asymptotes, things like that. Then we're going to move on to the derivative. And from the derivative, we're going to be able to determine things like when is the graph of the function increasing, when is it decreasing, when are there extreme values, maximums and minimums. Then we're going to move on to the second derivative. And the second derivative is going to tell us when the graph of the function is basically the shape. When is it concave up? When is it concave down? When does it change concavity? What are the inflection points? So we're going to go through this step by step. First we'll work with the function, then we'll work with the derivative, then we'll work with the second derivative. Okay, so what does the function tell us? F of x equals 3x to the 2/3 power minus 2x. Well, let's start with the easy one. What is the y-intercept? Well, for the y-intercept, we plug in 0 for x. So f of 0 equals 3 times 0 to the 2/3 minus 2 times 0, so 0. So we have a y-intercept of 0, 0. All right, what about the x-intercepts, if there are any? Well, for the x-intercepts, we plug in 0 for y, or set the function equal to 0 and solve. So we're going to solve 3x to the 2/3 power minus 2x is equal to 0. Let's see, we could factor out an x here. Well, let's actually factor out an x to the 2/3 power. X to the 2/3. And so we're left with a 3 minus, forgot the 2. 3 minus 2x to the 1/3 power is equal to 0. All right, so we have an x-intercept when x to the 2/3 is equal to 0, and that's when x is equal to 0. We already have that point. That's also the y-intercept. So 0, 0. And we also have to solve 3 minus 2x to the 1/3 equals 0. Or 2x to the 1/3 equals 3. And let's solve for x. So divide both sides by 2. So when is x to the 1/3 equal to 3 over 2, and we'll take both sides to the 3rd power, so we get x equals 27 on top, 8 on the bottom. All right, so we have an x-intercept of 27 over 8, comma 0. So that point's going to be on our function. Or on the graph of our function. Okay, so let's separate that. What's the end behavior? Are there any horizontal asymptotes or slant asymptotes, or does the function approach positive or negative infinity on the right or on the left? And to find the end behavior, we have to evaluate the infinite limits. The limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. All right, so let's look at behavior on the right. The limit as x approaches infinity of 3x to the 2/3 power minus 2x, and let's actually use the factored form. X to the 2/3 from above, x to the 2/3 times 3 minus 2x to the 1/3. So as x goes to infinity, x to the 2/3 goes to infinity. And as x goes to infinity, the 3 minus, well, the 3 doesn't really do anything when we're talking about infinite values, but the minus 2x to the 1/3, well, x to the 1/3 goes to infinity, so it's minus 2 times infinity, or minus infinity. So we have an infinitely large positive number times an infinitely large negative number, which means we're going to, that should be negative, we're going to negative infinity on the right, or negative infinity as x goes to infinity, and the limit as x goes to negative infinity of x squared, x to the 2/3 times 3 minus 2x to the 1/3. And so if we plug in, well, as x goes to infinity, x to the 2/3, well, we're squaring those values. So they're large, very, very large negative values that are being squared. So again, that goes to positive infinity. And when we take very, very large values to the 1/3 power, so the cube root of a large negative number is still a large negative number. So, and because we have a negative sign here, a minus sign, so minus a minus infinity or positive infinity. So an infinitely large positive number times an infinitely large positive number will be another infinitely large positive number. So on the right, the graph is going to negative infinity. On the left, the graph is going to positive infinity. Now, what about discontinuities? Well, there's no issues with this function. The domain is all real numbers, so there's no holes, no jumps, and no vertical asymptotes. So no discontinuities, or more specifically, no holes, no jumps, and no asymptotes. All right, so I think that's about all the information that we're going to gain from the function itself. So now let's move on to the first derivative of the function. All right, so let's say f prime of x, the derivative. Well, if we take the derivative, we'll have a 3 times 2/3 x to the negative 1/3 power. And the derivative of the minus 2x is a minus 2. And so it looks like the 3's cancel. So we could simplify this to, let's say, 2 over x to the 1/3 power minus 2. All right, so there's our derivative. So our critical values, the places where there might be maximum or minimum values, is when the derivative is equal to 0 or when the derivative is undefined. So we could start off by saying the derivative is undefined when x equals 0, because we have an x to the 1/3 on the bottom. So if we're setting this equal to 0, the derivative is undefined when x is 0. So that's one critical value. So that's a critical value. And when is the derivative equal to 0, well, let's solve 2 over x to the 1/3. I'll add 2 to both sides is equal to 2. Or when is 2x to the 1/3 equal to 2? And that's true when x to the 1/3 is equal to 1, or when x is equal to 1. All right, so that's our second critical value. So we have two critical values. So the derivative is equal to 0 when x is 1, and the derivative is undefined when x is 0. So now let's apply the first derivative test to determine whether or not there is a maximum, a minimum, or neither at each of these critical values. So let's go back to blue. The first derivative test. All right, so let's look at a number line, and we'll plot those critical values. So we have a critical value of 0, and we have a critical value of 1. So let's plug in some test values into the derivative. So let's say when x is equal to, we could say -1, we could say 1, and I'm going to use 1/8 as our test value between 0 and 1 because we're taking the cube root. So I want to take the cube root of something that's relatively easy to do, and the cube root of 1/8 is 1/2. All right, so we'll use these test values. So what is the derivative? What is the value of the derivative when x is -1? What is the value of the derivative when x is 1/8? And what is the value of the derivative when x is equal to 1? Oh, sorry, not 1. Let's use 8 there. We can't use 1. 1 is already the critical value, so let's use 8. All right, so we're plugging these values into the derivative, which is 2 over x to the 1/3 minus 2. So if we plug in -1, we get 2 over a -1 minus 2. So that's -2 minus 2, which is -4, which is a negative, which means the function is decreasing. All right, so we could say the function is decreasing here. Now, let's plug in 1/8. Well, the cube root of 1/8 is 1/2. So we have 2 over 1/2, which is 4, and 4 minus 2 is 2. Function is positive, or the derivative is positive, so the graph of the function is increasing, or the function is increasing. And if we plug in 8, the cube root of 8 is 2, so we get a 2 on the bottom. That 2 over 2 is 1, so we get 1 minus 2, which is -1. The derivative is negative, so the function is decreasing. And since at x equals 0, the function changes from decreasing to increasing, there's a minimum value. So what do we know? We know the function is we know where the function is increasing, we know where the function is decreasing. So the function is increasing on the interval 0 to 1, and the function is decreasing, -infinity up to 0, and is also decreasing from 1 to infinity. And when x is 0, we know that y is also 0, so the point 0, 0 is a minimum, because the function is changing from decreasing to increasing, so down then up, so there's a low point there. And when x is equal to 1, the function itself, so if we plug in 1 to the original function, we get 3 minus 2. So it's 3x to the 2/3 minus 2x. So if we plug in 1, it's 3 times 1 minus 2 times 1, which is 1. And that's a maximum. All right, so we have our extrema. We have our intervals of increasing and decreasing. All right, and that's what the first derivative tells us. All right, so we've done what we can with the original function. We have our intercepts, we have our end behavior, we have the fact that there's no holes, jumps, or asymptotes, the domain of the function, and we should probably write this also, the domain is negative infinity to infinity, and that's a result of there being no discontinuities. Then we work with the first derivative. We got our extrema and the associated points, and we have the intervals of increasing and decreasing. So now let's move on to our second derivative. The derivative of the derivative. So we're taking the derivative of this right here, the derivative of 2x to the negative third minus 2. And so our second derivative is equal to negative 2 divided by 3x to the 4/3 power. So according to the power rule, if we take the derivative of the derivative, the negative 1/3 comes out front, so we get negative 2/3 x to the negative 4/3, and we'll put that negative exponent on the bottom. Okay, so inflection points can occur when the second derivative is equal to 0 or undefined. And we know that the second derivative, f double prime of x, is never equal to 0, but it's undefined. It's undefined when x is equal to 0. So if you plug in a 0 on the bottom for x, you get negative 2 over 0, which is undefined. All right, so there's no inflection points because the second derivative is never 0. But so let's look at intervals of concavity. So the only place concavity could change is when x is equal to 0. So let's plug in a test value, let's say negative 1 and positive 1, to look at the sign, when the second derivative is either positive or negative. The only time it could switch signs is at 0. So we're going to do f double prime of negative 1, and we're going to do f double prime of positive 1. So if we plug in negative 1 into the derivative, we get a 3 on the bottom, because we're taking negative 1 to the 4th power, which is positive 1, and then the cube root of that is positive 1, so negative 2 over 3. And since the second derivative is negative, the graph of the function is concave down. Now on the right of 0, if we plug in positive 1, we get the same negative 2/3. And if the second derivative is negative here, again, it's concave down. All right, so we have our intervals of concavity. It looks like the function is concave down everywhere except when x is equal to 0. Okay, so now let's go back through the information that we have so far. So we have these points from our derivative, or from our function. we have the x-intercepts and the y-intercepts. All right, so the point 0, 0 is both an x and a y-intercept, and the point 27/8, 0 is another x-intercept. Let's go down here. Let's start putting this information on our graph. Okay, so we have an x and y-intercept at 0, 0. We have an x-intercept between 3 and 4. That's at the point 27/8, 0. This is the point 0, 0. So those are our x-intercepts, y-intercepts. We also have a maximum value when x is equal to 1. That came from the derivative. So the point 1, 1 is a maximum. All right, so now what's happening between these points? So let's look at the number line. Let's say, what is the function doing from negative infinity up to 0? What's the function doing between 0, which is the minimum, or 0, 0, which is a minimum, and 1, 1, which is a maximum? So what's the function doing between that minimum and the maximum? And what's it doing between, let's make this a little bit longer. What's the function doing between that maximum and the x-intercept? Which is 27/8. And then from that x-intercept off to infinity. So what we know so far is that the function is decreasing from negative infinity to 0. We also know the function is increasing from 0 to infinity, or sorry, 0 to 1. And then we know the function is decreasing from 1 to infinity. So decreasing in this interval, decreasing in this interval. Now, we know it's concave down everywhere, except we have this issue at 0. So concave down, and concave down. So what we have to do is basically connect the dots. Connect the points in such a way that the function is decreasing where it should be, increasing where it should be, and the concave down where it should be. So it looks like from negative infinity to 0, the graph is concave down. So the only way to draw that is maybe something like that. Concave down and going up to the left. Then between 0 and 1, the function is increasing, but also concave down. So we have this sharp turn here. It's a saddle point. Then from 1 to 27/8, the function is decreasing, concave down. So it's going to continue going down, but concave down. And then in this fourth interval, from 27/8 to infinity, the function continues to decrease, concave down. All right, so that about does it. This was a long process, but this is putting together quite a few topics that I've talked about on previous videos. First derivatives, second derivatives, increasing, decreasing, critical values, extrema, inflection points, concavity. It all comes together in this problem. All right, so I hope this was helpful. I know there was a lot in this one single problem, but this is where sort of this whole idea of analyzing graphs or applications of the derivative sort of come together. All right, I hope this was helpful.